right? You can find it. Yes? No answer is yes? Okay. Now,
Are you going to post the solution to the exam, or should we just go to you for the couple?
yes. I'm not posting the solution because I'm not very creative, so I'm afraid I won't really have too many.
Yeah.
But you can always come, and a lot of it is a repetition of the quiz that we solved, and please come and talk about it. I've also opened a new question and answer forum on Angel. So if someone sends me a question, I can post it there and everyone can see it. I've never done this before. I want to try it to see if it works. Maybe Angel is better than its reputation. Okay. So did anyone get a chance to read the paper on SAFT? Honest answer is no. Okay. Let's recap a little bit from last time. Look at this slide in front of you. Let's have a discussion and remember what this was. Which method we are talking about, which reconstruction or imaging method it is. What are we looking at?
This is where we put all the different stands together.
Right, so what did we call it? Last time we talked about tomography. Tomo is the Greek word for section, graphy is drawing. It is put together an image of the interior of the object. And I showed you this example of a concrete samples where we have 9 emitters, 9 transducers, and you see here rays. For tomography, one way to do it is to use a process called ray tracing. So it's a very simple method. You assume that the energy is propagating along lines, which is an approximation. It's actually bands, but they don't consider it. And do you remember what's the difference between these two images? Try to think a little bit. They are both tomography. What's the difference between them?
One says one of them is velocity, one of them is intensity.
Yeah, so exactly. So when we have... Hi.
I'm so sorry, I got lost.
Dr. Brennan?
I'm so sorry.
I'm sorry, I waited a little bit, but then I didn't know it.
I was like going up the 3rd floor and all the other buildings, and I just have never been on that.
I'm sorry. I started on time.
No, it's fine.
And it's all being recorded. So, okay, so this is a source, the signal, this is what we receive. And you have learned that also in the lab and also in the homework, in other discussions, that we can extract at least 2 parameters. One is travel time or velocity, and the other is attenuation. You calculated attenuation coefficient recently a few times. By the way, if you have your homework, please put it here. So when we do tomography, we can use either parameter. You reconstruct either travel time or travel time delays or attenuation. So this one to the left, A, is based on velocity, and the other one is attenuation. And it's kind of well known that when you have a defect like that, so this is a concrete block that we talked about last time, and there is kind of a defect inside, it's simulated, that the attenuation is more sensitive than velocity. Okay. And then we talked...
Is that always true?
Yeah, when you have cracks and so here it is like polyester, which is typically we use it to simulate void. It's a very idea. So the attenuation shows, a little bit better location for this defect.
That attenuation is more sensitive to defects than velocity.
But why don't we use it? We even discussed this last time.
The accuracy. are those amount of factors that?
Exactly, it's hard to calculate it. Why? I gave you an example. Do you remember? I gave you a very concrete example why it is hard.
Equipment. You mentioned the equipment.
In which sense?
Kind of consistency.
That's good. So if it's not calibrated, very good. So if these transducers, if all these sensors are not well calibrated, the attenuation at one is not equivalent to the attenuation you get from the other one. So for those of you who know Jacques, who is almost everyone, he's now making an imaging system like that, and this is one of the problems he has, because he's making his own sensors, and of course they're not calibrated. So to measure attenuation, it's a big dilemma, right? To do it correctly. So that's why everyone sticks to velocity. I said something else too last time.
And the coupling and pressure.
Exactly. So if you have more coupling, it becomes better. If you just press the two transducers together, so if you have a situation like that, and for whatever reason, the pressure on the back of one of the sensors is more than the other one, it looks as if the attenuation is actually less, which is not true. So because of all of that, also attenuation is more sensitive than velocity. Somewhat people stick to velocity because it is free from a lot of these effects, except for nonlinearity that we have talked about. So this is a recap of what we basically stopped here last time. So this is an example in non-destructive evaluation, concrete. How about site characterization? So what we are looking at is tomography in the field. So if you are doing tomography in the field, in geotechnical or in site characterization, typically, to put the transducers, you have to have kind of a boreholes. So you drill a hole and you basically lower down your transducers, which will be geophones most of the time. They are called geophones, lower frequency, they measure velocity, etc. So here is actually a numerical model first. So numerical model, we start with a model with 4 different velocity. You can see V sub P and Q. What is Q, remember? Have you seen Q before? Yeah, there was something about Q factor, right? So it is nothing else but that. It's a measure of damping. Here they have used Q factor as a measure of damping. So 40, 80, 40, 100. And then you have source. A series of source here, a series of receiver here. That's just a snapshot of how the arrival times look like. This is kind of expected, right? Here is the source. Here are the receivers. As you go further, the wave arrives later, right? But also because the velocity is different, it's not linear. You see a curve. And here are a spectra for each of these. So in this paper, which is also on Angel as an optional reading, I told you last time, they have used really the spectra to calculate Q factor. That's actually the main innovation in this paper. So, and then we do a Q tomography, which is a form of attenuation tomography. So this is the model, the solid line, and the dashed line is what you get from tomography. Probably this is not as it's not as interesting as looking at the field data. Let's see what we are looking at. This is field data. So we have A, B, C, and D. So here is receiver well. So we have 2 boreholes, okay, 620 feet apart. So this is the receiver. Here is the source. So here we don't call it array or ultrasonic or anything like that. The terminology is different, but the concept is exactly the same. What you see in A and D is something which is called a sonic log. For those who are rock mechanics people, do you know what a sonic log is by any chance? Yi, Sheng? Have you heard about it? It's fun. Yeah, exactly. It's inside the well. So typically what people do when you create this borehole, the traditional way to measure velocity is basically this point-wise measurement. So you lower down a, let me change the color. You lower down some sort of a tube with a source on the top and a source at the bottom and a few geophones in between, receivers.
That's more common in well testing. Scratch proof.
Yeah. Yes, you are not a seismologist. Right. Okay. You know how when you are in a different field, you think the other person who does anything with with rocks, they know everything about that. But you're right. So you may have heard about it, right? So this is of course kind of destructive. You send it, and then from the reflections at the boundary, you kind of get an idea what is the velocity variation close to this well. So it is destructive, it's traditional, people all know how to do it, you don't need to do any fancy analysis, but you only get information from near the well. So let's look at these two. This is for this well on one side, and this is for this well. So here is going, velocity is going from 11 to 22. So basically this is the profile. For civil engineers, you can think about CPT. It's kind of similar concept, if you may, that you know how you deep down. Here, instead of measuring the strength or resistance to the cone penetration, here you measure velocity. So here are the velocity variations, and here. So now, in this case, we have used also receivers and source here to do tomography. On the side B, this is velocity. On the side C is Q. So here is velocity. Here is Q, which is attenuation. It is kilofeet per second. For civil engineers, this is a strange unit, but the wave velocity in earth materials are much lower, as you can see. That's why we don't use like other units. It's a typical unit in geophysics. Now, what's the significance of that? Look at the velocity and attenuation tomographs. In particular, let's look at point A and B. So in both, we see that, the darker colors means lower velocity or lower Q. In both cases, we see that, in both areas, for example, velocity and Q are low. But generally speaking, the two are not identical, right? So they are giving us different information. And they are giving us more information than just around the well. So, for example, if we focus at point B, you see that here the well on the source side shows a drop in velocity. But on the receiver side, not really. Also, we see that at B, the velocity is low. But near the receiver well, apparently it's not. So the point is, it's giving us a lot more information about the site. Correct? You agree with me? And then, when you have both velocity and attenuation, there is a process called data fusion. Maybe you have heard the term. You may be able to combine, to marry both to characterize the site better. That's a science of its own, but you have more information, so you will get more reliable characterization. Okay, this is all I have about tomography.
I'm sorry, so before you say it's very cute.
No, I didn't say it's better. I said they provide complementary information. They are not completely identical. So if you bring them together, you'll be able to characterize the subsurface better, because you may have, let's look at it this way. You may have a lot of different rocks with the same velocity, but they may not have at the same time the same attenuation in the same range. So that will, if you have both information, that will help you to discriminate one from the other. Makes sense? And that process is a mathematically intensive field called data fusion. So you have multiple sources of information, you bring it together to, this is one area I've worked on recently quite a bit. Mm-hmm.
So providing those two profiles, you cannot say which one provides you a better result.
No.
You only have to combine all of them to make a decision.
Exactly. If you combine them, you get more reliability, right? Because you may have different rocks which all have, velocity in the same range, but their attenuation properties may be different. And if you have only velocity information, you would not be able to say one from the other, right? But if you also have attenuation, then you can say, oh, this is this one. That's the purpose of site characterization. You want to know what types of material you have underneath without doing it. But I also hope that you see the analogy between site characterization and non-destructive evaluation. It's just the scale is different, right? Everyone agrees with me? Good. So here we close the topic on tomography, which can be really its own course. And we go to the next imaging method. So if we remember from the beginning, we said we talk about scanning, A scan, B scan, C scan, D scan, correct? And then we talk about tomography and SAFT. And now we want to kind of introduce SAFT. Okay, why do we need SAFT imaging? Why B scan is not good enough? Maybe before that, we kind of have to review what B scan was. So here is my transducer.
Do we have this slide?
No. It's not very important. It's more review of what we had before. You are moving it. So do you remember the difference between A scan, B scan, C scan, D scan? Is anyone brave enough to?
From different sections.
Right.
From top, side, and that.
Exactly. How about A scan? What was A scan?
It's a single point.
Right. A time signal. B scan. If I do that, whatever I get, as Sheng pointed out, this will be like a B scan if I cut the plane like that. And if I cut it in the other direction, we can call it D scan. And C scan is plan view, but not plan from the top, but inside the material, when you slice it horizontally. Okay. Now, the problem with B scan, basically all of these scans, the main issue is that, especially in rocks and concrete, we have a lot of something which is called structural noise. We talked about the scattering. Now, what we are seeing in this picture are different snapshots of propagation of a transducer as it meets a delamination. So here are like different time. It is as if a movie is, we are looking at time 1, time 2, time 3, time 3, time 4. So the transducer is emitting, and then you see the wavefront, and then it's moving in the next time step because it's wave propagation. It hits the lamination. What is happening here? Why is it changing direction? What did we call this phenomenon? A wave comes? Yes, reflection. Right. A little bit is refracted, but because you have a delamination, almost everything is going back upward. And then here. So, what do we see here? I mean, what are these little ripples?
Is it a wavefront or is it a wavefront?
The ripples, the wavefront is here, but the thing that you can kind of see it's moving. Correct? You see that something is moving in this picture. It's a video. That's the wavefront. And we see it's strong under the transducer, and not so strong here. Oops. And but what are these? Why do we have all those little dots inside of this?
Scattering?
Hint, this is concrete, exactly. So the wavefront is the coherent part of, so then everything works together. But concrete has a lot of heterogeneity. Each one of those little aggregates is reflecting a little bit on its way. And if you visualize it like that, this is a finite element simulation from my colleagues, former colleagues at BAM. You see that you have a lot of scattering noise. This is collectively called a structural noise. Why? Because it's coming from the macrostructure of material. And because of that, there's one other thing I want you to pay attention. I kind of mentioned it. Pay attention that the strength of the wavefront is not uniform. We had talked about a spherical wavefront, right, for P wave, S wave. But here you can see that it's obviously much stronger underneath and kind of fades towards the end. Because transducers have directionality. Because of these two problems, B-scans are not the best kind of imaging in concrete. Now let's look a little bit more closely at this.
What kind of scans are not the best?
B-scans.
Okay.
Mm-hmm. So B-scans are, those which you have seen it even in the lab, and I showed you Mira. Remember those? Just B-scans are a stack of A-scans. Then you color it. Okay. So here now we want to see why it's better to apply use an algorithm to image. So the algorithm is called Synthetic Aperture Focusing Technique, SAFT. Please read this. I know you didn't read it before this class, but this is a mandatory reading. That means I can ask questions from it. It's a very easy read. When you go, to relax somewhere, just take it with you and read it. Okay. Now we want to talk about this algorithm. Okay, this is where we start. We have a transducer. This is a concrete block. The maximum aggregate size is 8 millimeter. It's kind of important, this parameter, in the subsequent discussion, so I write it down. Maximum aggregate size. And we have this transducer, and in this concrete, we have drilled 2 holes. You see the diameter, you see the location. This is the depth. Everything is in millimeter. So Now, let's first focus on this. What's the technical term for this again? What type of a scan is it?
You mean the loss?
Yes, the time signal. It's an A scan. It's an A scan. Let's understand this a little bit better. How did I call this process when you have one single transducer with an emitter and receiver inside moving on top of a test object? What did I call this? What we did in the lab was through transmission. What did I call this? What did we call this? Remember? Something echo, correct. Not impact echo. We don't have an impact. What do we have instead of an impact? What gets echoed? Acoustic echo, good. Emitter echo, we are getting close. Pulse echo. Pulse echo. And everyone says, yeah, we have heard this before. They say the best way to learn something is to recall it. So that's what I'm trying to play with your recalling. Okay. Now, this is a pulse echo. That means that it is like the transducer I showed you. Remember 1212? Right? It has a sender and receiver at the same time. So we are moving this along. Now, I tell you that this A scan was taken, so this is the axis, at 120 millimeter from the lower left corner of this. Somewhere here. Okay. What do we see in this A scan? Why not just using this the A scan? Can we use it to find the hole? So remember, we are in a situation where we want to find where those holes are. Our concrete slab is holed. We don't know where it is. We have this transducer. We go, we do this test, and we want to find out where this hole is. That's the whole objective of doing this. Now, we have this A scan here. If we had only this A scan, what could we say? What does it show us? What do we see in this A scan? This is what we want to find out. If I give the velocity of this block, the p-wave velocity 4360 meter per second, it's concrete. Where would you expect to see the echo of the left hole? Take out your calculators and tell me, where would you expect in time to see the echo from the left hole?
So it's in 199.
It is 199 from here, the center. And it is 191 from the surface. A little excess. Where do we expect to see the echo from the left hole? Yes.
So is this stakes using this loose though?
Yes.
So like
But I've told you that this is at 120 millimeter.
okay.
If it was on top of it, where would you can just estimate it if it was just on top of it. Don't make it complicated. If it was on top of it, where would we expect to see it? Does anyone have a number for me?
8.8 times 8 turn all the way to 5, all the way to negative 5.
80?
8.8.
So 80 microsecond.
Yes.
Okay. About 80, 90 microsecond.
87.6 actually.
This is, where did you put the transducer?
Exactly the top of that.
Okay. Did you consider that the travel time is 2 times?
2 times.
Okay. So you expect to see the transducer at 86, 87 microsecond. So this is, I just wanted you once to have experienced that. We have talked about it, but you have to double the distance. That's the whole point. So it is 2 times this distance, whatever this distance is, divided by the velocity. Okay. Now, look at the A scan. So this is kind of where you expect to see the reflection, correct? And what do you think is the large reflection we see? So this is coming from the hole. What do you think this other big indication is coming from?
The lower boundary.
Yeah, the back wall of this slab. So the same way you can calculate where you expect to see it. If you have a pulse echo measurement, this is how you interpret it, pretty much. Okay. Now look at the other stuff in the beginning. So what are these?
So what
Yeah.
does that wall mean?
Back wall is here, the back wall. This is a term, like a special kind of term. It's the back wall or the back of the slab. But we say back wall, everyone would say.
The part that you said called is just the first hole? Or
So your transducer is here. Right, it's somewhere here. This is the AS scan. This is a real AS scan from a real measurement. We kind of figured out, or you did it actually, that you expect to see a reflection from the hole between 80 and 100, somewhere like that. And then this large reflection that you can see is coming from the back wall. It is here, right? Now my question is, what are those we are seeing in the beginning? Think back at this slide I showed you.
Reflected by the aggregates.
Right. Believe it or not, that's all the structural noise, surface wave, all those of things, and you see they are not insignificant. So,
all of that is just noise?
yeah. Because concrete is a very hard material to work with for undestructive evaluation. If this was metal, you wouldn't see anything. And then you would see it's beautiful. But this is a heterogeneous material. Every single particle is reflecting a part of the energy. And of course, if they are closer to the source, they are doing more. And I'll tell you in a moment that near the transducer, there are some really crazy things happening. So the transducer has a near field where things are very crazy. So that's why you also see a lot of noise here. And if you compare this, you know how to calculate signal-to-noise ratio. If you compare this, you see that the signal-to-noise ratio is not very great. And remember, this concrete has a very small aggregate. If you are the civil engineers in the room, you know that 8 millimeter concrete, it's very small, right? You agree with me? So even that, you have this kind of noise. Where do I get from here? I just want to tell you that if you only have an A scan, it may not be enough. It's just, it can be too noisy, as you can see. And pay attention to a few other things that, as the signal, if we look in time, we see that we are losing high frequency components. You see? Please read this paper. In a very simple language, they have explained these concepts again. It's a good reinforcement for the thing we have talked about. Signal broadening, sometimes it's called. But basically, the high frequencies gets attenuated, as you have seen in the lab, right? Faster. And gets easily attenuated. Remember, think about your 100 kilohertz and 250 kilohertz experiment, correct? There is one more thing I want you to think about. This is the last one. And this is, why do we actually see? Why do we see? We are at 120. This hole is 199. Why do we see a reflection from this hole? That's strange, isn't it? The hole is at 199 from the lower left corner, and I'm telling you that this A scan is recorded at 120. That's 7 centimeters. But there is an indication from the hole. Why? How could this happen? This is an error. Okay, let's go back at the previous slide again. This is the wave field for a transducer. Do we have wave field only underneath the transducer? No. It's a stronger just underneath, but we also have it. So it is like a cone shape. The transducer, it's very strong when you look down, but then it still has some strength, and then it fades. And this is the problem, or this is the phenomenon that you see here. Even before you get here, you start seeing the object. So this is kind of a very, very important concept. And that's what you will see if, this is from an older paper, but since it's the first one who talks about this, I have included also the graphics are not that beautiful. So here is the transducer. So under the transducer, this is kind of a schematic showing you that we have a zone. So even if the transducer is not directly above the object, we kind of see it. So now if you move if the object is just one point and you move the transducer around it, what do you expect to see? If you go just above it, the distance is minimum. As you go to the left or right, the time distance becomes larger. So you get this hyperbola. And this is what you are seeing here. And it's very easy to calculate the equation for this hyperbola. So I call it apparent depth. Because if you are here, you think that your object is here, right? If I only have this one trace at x1, correct? Yes. You don't know. Make sense? And this is basically from what you see here, it's the square root of delta x squared. That's the lateral distance to the real location, plus d squared. That's the real location of the object. That's what you see, this hyperbola. that's the essence of SAFT. So what we try in SAFT to do is to replace this hyperbola with the point, to find a way to correct for this. So instead of seeing these hyperbolas in the images everywhere, you actually see the exact physical location of the objects. That's basically the essence of this technique. Now, before talking about SAFT, since this is very important, let's talk a little bit more about what I told you about the transducer. This is a very important concept. So when we have a transducer like this, which is not an ideal point, you have this kind of field. Let's focus on the picture on the top. So you have a transducer. Very close to the transducer, there is a zone where it's called near field. That's where the beam is kind of cylindrical. It has a diameter slightly smaller than the diameter of the transducer, and then starts to spread like that. So when you look at any of the transducers in the lab from now on, never think that they are sending down a tube of energy. No, they are sending this kind of energy zone. And it's not like, it is, here is 5, here is 0. It fades, as you can see, it fades very smoothly to the end. Now, near the transducer, this zone, because every transducer that we have, every single point is generating a pulse. Okay. And since the surface is big, these pulses, they have kind of destructive, constructive pattern. And near the transducer, in the near field, that leads to kind of a chaotic situation where there is a lot of fluctuation in the intensity. So you have to avoid using a transducer in its near field because we don't know exactly what is it measuring in terms of amplitude especially. It still reflects back, but in terms of amplitude, it's kind of chaotic. And then we have the far field where it becomes linearly divergent. So we have this angle delta. It's possible to calculate or estimate the length of the near field zone, and the equation is d squared over 4 lambda. D is the diameter. So it is more severe the larger your transducer is, basically. And lambda is the wavelength of the transmitted pulse. So the same diameter, if the frequency is larger, what do you expect? The near field zone is longer or smaller? Right. So frequency is larger, lambda is smaller, so near field is larger.
So you don't want to be near field?
No. You want to avoid it. And you always have to kind of know your near field in any material. As you can see, it depends on the material you are testing to. So you don't want to make any attenuation measurement, anything which has anything to do with the amplitude measurement in near field. Absolutely not, because it's unreliable.
You exclude part of the signal that's from the near field.
Mm-hmm.
So how
You
do
still
know-
see reflection. Mm-hmm.
So like,
We can calculate it very easily.
so this gives you what?
The Z.
That distance?
Right.
And then how do you determine that with, like once you have that Z, what do you do with that if you're looking at your signal?
You know that if an object is within that distance, so this transducer is on the floor, right? So here, it's on the floor. You know that in this field,
Okay.
if you are looking for something, you won't be very accurate, reliable results. I mean, attenuation is a no-no. You can't measure anything. Because look here, it's just giving something.
Okay.
Yeah.
So we need to make sure the depth of whatever we're looking for is bigger than that Z.
Yeah. Sometimes people call this the blind zone of a transducer. It's like, here
My
is
question
blind.
is, how do we see it though? Like on the previous slide, like just that signal we were looking at. How can you identify it in a signal? Like for example, that.
It is somewhere here.
It is, okay.
Yeah.
So it is, okay.
It makes, yeah, so basically those aggregates which are very close, they disturb the near field. And you see it in the beginning of the signal because it gets reflected back. Mm-hmm.
How come we didn't see that in like the stuff that we did in the lab? How come we weren't excluding any of the really early stuff that we saw in our signals? Or
In the lab? What do you mean?
so
But you weren't working in near field. You had like 3 inches. We will measure the near field of the transducer. You see it's only a couple of millimeters.
okay,
So, and then you see those ripples, those small
okay.
things in the beginning, the noise you have. So
Okay.
you see.
So if you had a poorly designed transducer or something, that would be further into your signal and would be, I guess, a worse signal.
If you have a poorly designed transducer,
Right, like you had one that was too big.
then it would be worse.
Yeah.
Right. Yeah, absolutely. You always have it. This is not something you can.
It's not something that I noticed in the stuff that we did.
But you have noise in the beginning, right? Where is that
Okay.
noise coming from? That's
Okay.
that's a part of it.
So it's part of the noise.
But we didn't have anything which was in the near field in the lab, right? We will calculate in the next slide how much it is, so you get a sense how long that is. But we haven't worked on anything which you need to work in the near field. But you see that noise in the beginning.
Okay.
You have some noise.
I have a question.
Yes.
So actually, where does the wave actually transmit or generated? It is from the surface of the transducer.
Mhm.
So actually, I'm thinking about in the lab we will do the through transmission.
Mhm.
The test is more like in the near field.
No, we calculated exactly. It is not that large. That's exactly okay. We calculate now the near field. This is exaggerated. It looks large here, but it doesn't have to be large. We calculate it right now. Okay, just after this slide. So you see that it's not that large. But if you remember when Giancarlo wanted to test, you remember that when I saw the very small specimen, I told you we can't use this big 100 kilohertz transducers. This is exactly for that reason.
Oh, okay.
Because whatever you measure, if it was only 1 inch thick, right?
Yes,
This
it's
remark.
1 inch.
So that's those 100 kilohertz are really large. So at that time I didn't explain it to you, but this is what I was thinking about.
Oh.
2 things: this and wave guiding, which we haven't talked about yet.
The near field constant, like can I think of it like you have a transducer that's always going to emit this beam, like this zone, regardless of what material I'm using, that near field is always going to be the same for that transducer?
No, because it's also because of this lambda, it also it's
So that's
also
not the
depends.
frequency of the transducer?
Lambda is a velocity over frequency. So this velocity is a material property.
Oh, I thought that was the frequency of our transducer.
No.
Okay.
Exactly not. So that's a good question. So this has something to do with the geometry of the transducer. But so why do people don't talk about it when they talk about the theory of wave propagation? Because all the load is considered point. So we don't have to deal with any of that. This is when you go to the practice of using ultrasonic transducers. Because if diameter is 0, if it goes towards 0, this zone really doesn't exist, right? Makes sense? Okay, and there is another parameter here, very important, and that's actually we have all this discussion about near field, but What is very relevant to SAFT is this divergence angle, for obvious reasons, right? Let me ask you this. If I tell you that divergence angle also is proportional, or it is a function of lambda and d be the diameter of the transducer, lambda the wavelengths, how do you think the proportionality is? For example, do you think delta is proportional to d or 1 over d? In other words, if the transducer is bigger, do you think it has a larger delta or a smaller delta? And then the same applies to lambda. Larger? Why? It's easier to talk about lambda first. So, lambda. Do you think it's proportional to lambda or proportional to the inverse of lambda? In other words, if the probe is higher frequency, is it more divergent or less divergent? So this angle is defined as when the intensity drops below 1/2. So you consider this delta from the maximum, where the intensity, which is maximum in the middle, drops by 1/2 the amplitude. 6 dB drop. So now, if you have a high frequency probe, lambda is a smaller. What do you think? Does it attenuate faster? Right? So it makes sense that this is proportional to lambda. So it's proportional to lambda over d. And the expression is, so delta inverse sine 122 lambda over d. This depends on how you define it. This is definition that the amplitude drops by 6 dB. Depending on how you do it, you get different parameters. So this is also for a material, for water, I think. This is how you can basically, you see that the diameter is here, the frequency is here. This is for water with sound velocity 1500. So you can see how it is changing. Basically, these are for different deltas and diameter and f, so you can find it. And here you see that, how the frequency of the probe is increasing and the diameter, and you can find it. We work normally in this range, so this is more for industrial applications. For concrete rocks, we are pretty much here. Now, yes?
For a large diameter, the spread is only 1 degree. For like 100.
Yeah, it can be very, very small. Mm-hmm.
Okay. So how wide is the initial beam? So
It's as
wide is the transducer?
a little bit smaller, but you can approximate. Yes,
So
exactly.
it's just, I see, and then it'll just slightly.
Look, it is slightly smaller than the transducer, and then the spreads. Now, because of all the questions you ask, I'm glad that I have this example. Now let's calculate and see what these numbers are for the type of measurements we have done. Let's just take 200 kilohertz P-wave transducer. We didn't have 200 in the lab, so let's just take 100. P-wave transducer we have had in the lab. Diameter,
Speech.
3 inches? No, 3 inches is... It's yeah. I've taken it at 40 millimeter now. So let's calculate what would be the near field and what is delta. So we it becomes more tangible. That for our measurements, what type of angles and near field we are actually talking about. You have a question? I have the numbers for 200, but let's do for 100, and for you it's more tangible. So this is near field will be E squared over 4 lambda. So we need to first calculate lambda. And let's take the VP 4000. For concrete. Oh no. Okay, let me clarify that. This I just gave you, to have it in your notes. This is a graph for water, and this is the wave because, as you know, this relates to wavelengths and not frequency. So with these two parameters, we can't have this figure. So this is here. Okay. Here we are not testing the water; it's just concrete. So 4,000. Lambda is, who has the lambda? 4,000. Thank you. So we have 100 kilohertz. Right? It's 4 centimeter, so it's pretty big, right? The wavelengths. Now, the near field, it's kind of easy to even calculate by hand. So basically don't worry about it. Okay, that's why we didn't have to worry about this. Because how large was the thickness you were measuring with this transducer? 80, about 80 millimeters. So don't worry about this. But if you were going to locate something within the first millimeter of concrete, you could have not. It would become complicated. Now, if in true transmission, you have to consider from both sides, right? Everyone is listening? If you are considering, because the same way that they transmit, the same way also they receive. So if you are having two transducers, 1 millimeter, that's why for Giancarlo, for 1 inch, it was very iffy to use this kind of transducer. Yeah, okay. And delta. What do we have for delta? Yeah, we can calculate it. Because lambda and d are equal, so I chose just the wrong number. So delta is kind of very large. But this is this factor is coming from the fact that where you cut it. So I guess the diameter and lambda kind of. So delta is just very large here. Okay. Now, here, remember why we are learning that. So from the beginning, we kind of started here that when you do move a transducer next to itself, you get A scans and you have a lot of noise. So interpreting one A scan may not be a good idea. When you are moving a transducer above a point, then you get some sort of hyperbolic shapes looking like that. And the reason for that is everything we talked about here. This is spreading of the beams of these transducers. Now, the purpose is to see, what to do about this. So these are the situations. What should we do about that? Now, you recognize here at the bottom which scan. What do we call this scan? B scan. Please remember that. Well, this doesn't have really, the B doesn't stand for anything, so that's kind of, but this is what everyone calls it. So it's a B scan. B and D, you can kind of use interchangeably, but not with C scan. C is, think about like section, like I know it's with S, but kind of, I don't know. C is different from B or D. That's a bad mistake. And this is what we would get. This is also after a lot of pre-processing. So for the same specimen, if we do B scan, which means stacking all these A scans together, like you see here, do you recognize the echoes from the holes? Yeah, we see them, right? And also pay attention that they have the same phase. Like you have black, white, black. This is how you recognize the phase in a scan like that. Because it is like a wavelet like that. If you imagine that you color this black and this is white, so those are also holes. That's why we get the same thing. Okay, now we want to see how to make the image from this. We already talked about this concept, why we get that. So we want to see how to correct it. Okay, how do we correct this? Here we have a scan. It's kind of rotated 90 degrees. Yes.
What do you mean, what are we trying to correct?
So this is a B scan. Good question. B scan, we talked about this last time. We kind of can see the signatures from the two holes, and we see the back wall reflection. These are the terms we use: back wall reflection and signatures. What's the problem with that? This is, I think, Tiffany's question. What's the problem? Why not using this? It's great. No, I mean that's the argument. It's great. Why not? Stopping here and saying, this is a lot of. This is not a raw scan. If you can please read this paper, you see that there is a lot of pre-processing, and that's the best we can get. What are the issues with this?
The narrow resolution stuff, you have like
What do you call this resonance?
resolution.
Oh, resolution. I'm sorry.
You have two poles very close to each other, you may not be able to
Very, very, very good point. One thing is the lateral resolution is very poor. So you have these wide hyperbolas where you have only a hole like that. And then also you look at all the structural noise you have. So if the whole, one thing Jiang said, which is very valid, is if they're very close to each other, there would be no way to find out where they are. So your resolution is limited. But also, if this wasn't, that's a big hole someone drilled into the, this is a lab at BAM where I was working at. We just drilled a hole, and so if this was a real, not very perfect cavity, that is typically what you want to find, do you think it would be very easy to find this reflection? And even the location, exactly where it is not very clear. I mean, you can argue that wherever you get the maximum, or it is the closest to the surface, that's where it is. But remember, it's not like a continuous thing. You have at different locations. A BS scan in ultrasound, it's not like radar that you can go smoothly. Even radar, I mean, you have a certain interval, and then that also determines where is actually this hole. Is it here? Is it here? How big is it? We don't know. I mean, there are lots of things we can argue about. But also, it's good that now we came back to this figure. Pay attention that where we have the hole, the reflections of the backfold also are kind of distorted. This is another way that sometimes people, especially if this hole was in the near field of my transducer, maybe I would not see a nice reflection like that because of all the stuff we talked about. But from this, you would know that something is blocking the path of energy from the transducer downward. This is actually a method that people use also in industrial NDE to find very thin delaminations inside nuclear power plants,
This is
etc.
just pulse echo, so you're just taking a transducer and then you move it and then that's all this.
Absolutely. Yeah, this is all related to the same kind of experiments, pulse echo. Okay, now, good question, Tiffany. It's good I spend more time explaining why we are doing this. So now, we want to see how we correct for it. So the idea is to go from here to there. How do we do this mathematically? So the way to do it is just using the very simple, this is kind of rotated 90 degrees. Imagine that the location of each of these reflections is as a location di, like the thickness. And we have let's call this location 1 and 2. Now we are human beings, we're intelligent. We look at it and we know where the maximum is and so on. But to make an algorithm, we have to make it robust. So this is how it works. We kind of know that, I just showed you before, that this di is very easily related to the real location of the object, let's say do for the object, squared, plus the delta x. How far the point that we are measuring is from the real position of the object. Correct? Now, if we assume that the object is at location 1, so here is if the assumption is the object is at location 1. We make this assumption. What you do, you correct the neighboring rays based on this assumption, based on the relationship that you have. So DO becomes D1, and then you can correct everyone else's position. Right? When you correct them, how many we take on each side, that depends on the divergence angle of your transducer. So here we just took 2 on one side, 2 on the other side. And this size will depend on the divergence angle that we spend quite a bit of time talking about. So we assume that this is at this location, we correct it, and that's what we get. Now, what you do next, you calculate the correlation between these 5 rays. So you assume one is coming from the object. You take enough rays in a bundle corresponding to the size of your divergence based on your transducers. We learned how to calculate it, right? Okay. You correct the locations using this simple equation, and this is what you get. Now, you calculate the correlation between these rays. What do we get? If all the rays are aligned, the correlation would be maximum. If the location that we assumed is wrong, and they look like that, the correlation would be some small number. Then we know that this is not the correct location. If we take, instead of x1, the correct location x2, and we correct for the shift just because of the lateral distance from the real object, if we calculate the correlation, because everyone is aligned nicely, you get a maximum correlation. This is the essence of the algorithm. Think about it for a little bit, see if you have questions. Now it's just a concept. So basically, you go ray by ray. You look at the neighboring rays, depending on the divergence angle that you know from your transducer. We just learned this. And then you basically correlate. You can think about it as this. If you sum everything up, they cancel each other. But here, everything adds up. So here, we know that, yes, the object is there. This is basically how it works. Let me show you this figure. So this is the equipment you have seen. This is the data you have seen. So for every ray, this is not in your notes. For every ray, you look at the propagation, then you apply the divergence, you multiply it, and you see here it fades out. And then for each location, you just sum up all the reflections, and then you get the amplitude to see what you have seen before. This is how it works. So from that very noisy image that you had seen before, then you can exactly see where the objects are. It also has its own drawbacks, but for now we just talk about the good things, right? And then afterwards the limitations. Let's go a little bit back. This, I just wanted to give you an idea how it goes. So the algorithm works like that. So we have, let's say we have a echo, we have a B scan. This is in 3D. So a B scan, we have an X, Y location of the transducer and a time location for the point, right, inside the B scan. If this is a 3D, so we have X and Y. If it was 2D, it was only X and T. We basically sum up and normalize everything to get the soft image. So at every position inside, you look to see how many rays are arriving there, and you get the amplitude, and this is the summing up. If they sum up, you get a high reflection. If they don't sum up, you get a small reflection. And this TMN is basically from the same equation. The time distance from every point to the transducer location. That's the basic equation. Next time I show it a little bit more, the 2D version of it, which is more tangible. And then we are done with the imaging. Any questions? So this time is just this correction from the distance. Instead of using distance, if you use time, and you have 2, because it comes, gives, and goes back. We talk about it. We stop here, but we talk about this. We start from here next time.
Is this something you would use software for? Is this something you would actually have to write your own code for using these equations with your raw data that you collect?
Both. I mean, you can write your own, but there is no software. You see the paper I have given you, it's 2003. So it's not like an established method, not in ultrasonics. In radar it is, in ultrasonics it's a little newer. There are software like everything else, but you can also write between MATLAB. It's not very hard. There are a lot of details. When you want to really deal with it, there are lots of details. But in terms of concept, I hope that you all have some sort of a sense how it works.
So you can download a event collector to create a transducer during the course of that method, and you can apply all this and then it created, or not created, just adding on to the math.
Exactly, and you deconstruct it to have a better resolution with that. And this is, for concrete, this was developed in the institute I was working at not long time ago. But yeah, I think in metals they used it a little bit earlier, but it's coming from radar. People use it in radar more. And the funny thing is, you can imagine, the larger the divergence angle is, it's the better. Because you have more overlap between points. So if you have more overlap, your resolution becomes better and better, right?
Like the computations become more intensive.
Yes, I mean you have more points, but everyone has some clear idea about SAP?
Does Mira use the SAP?
Right. That's what I don't remember what happened, but that's what I first asked you to try to see, to do it. And people are still struggling with the phase which we did a long time ago, but I'll explain it. We'll start from here next time, and I dig it a little bit more into these formulations and how it can be used. There are a few